So, okay, so it's a great pleasure to welcome Steve Simon. He's been here many times before, but and this is his first virtual visit, I believe. So thank you for agreeing to give this talk, Stephen. And welcome. We are enthusiastically looking out to see what the latest news is.
Okay, thank you very much. It's going to be exciting to do this. I always enjoy visiting Ireland, virtually or otherwise. So I guess I should say first, please do interrupt me if I'm not clear. The talk is a little bit, it's aimed to be a little bit on the short side, so there's plenty of time for questions. The talk is sort of written for a condensed matter audience, so some things might need a little bit of clarification along the way. I hope I haven't left anyone too much in the dark. So, you know, yell, jump in and ask whatever you want. So the talk I'm going to give is about thermal transport along fractional quantum Hall edges. And in particular, we'll discuss a number of different fractional quantum Hall states, but the interesting experiments were in the so-called nu equals 5/2 fractional quantum Hall states, where not everything, some things came out very interesting and some things came out not the way we expected them. And there's still some controversy as to what's going on. So there's a series of 3 papers that I've written on this, and there's probably more coming. And still, we don't have necessarily have a unique solution as to what is going on in these experiments. So just to give you a, can you see the pointer? Yes, I hope.
Yes.
Okay, good. So the physics of quantum Hall edges goes back to the very, very early days of quantum Hall physics in the early 1980s. And it can be understood in, you know, the basic picture can be understood in a very semi-classical way. It's very simple. So here I've drawn the edge of a quantum Hall sample. So the blue is supposed to be electrons, and then you have an edge, and the white region is, you know, the vacuum of space. And so there's an edge where you go from having electrons to not having electrons. And we know that there is, it's a 2-dimensional sample, the magnetic field perpendicular to the plane of the sample. We know that there's an electric field at the edge of the sample, because if there weren't an electric field, the electrons on the edge of the sample would leak out, and they don't. So there's an electric field that's holding the electrons in. And then just from basic, you know, first year classical mechanics, whenever you have a crossed electric and magnetic field, you have a drift velocity for charges. And so if you make a little bit of a bump of charge, that bump will drift along the edge of the sample. I don't know if you can see that animation or not, but there's a bump running along the edge of the sample. And that's the basics of the quantum Hall edge dynamics. And so this has been studied since 1982, and then was studied in the case of fractional quantum Hall effects late in the 1980s and the early 1990s. And then it was realized that there's these quantum Hall edges have some really interesting properties, particularly by Xiaogang Wen and Kane and Fisher, and many, many, many more people have studied quantum Hall edges since then. I Googled quantum Hall edge and came up with 100,000 hits. That probably doesn't mean there's 100,000 publications, but it probably means there's 10,000 publications or something like that, each one being, you know, giving us 10 hits or something like that. So there's been an awful lot of study of quantum Hall edges and the properties. One of the most basic things we know about quantum Hall edges is that the electrical conductance, or the Hall conductance of the sample, is carried along the edge of the sample and is quantized in units of the fundamental constants, well, E squared and H, E squared the charge of the electron, and H being Planck's constant. A little less well known, but also true, is that the edge states also carry heat, as well as carrying electrical current. And the heat is quantized in units of these combinations, these constants. So T is the temperature, KB is Boltzmann's constant, H is Planck's constant, pi is pi, 3 is 3. In the integer quantum Hall case, the quantization is in integer units of these quantities, E squared over H, or in this thermal Hall conductance quantum. And in fractional, it is fractional units of these constants. Now, the proof that these things are quantized is not difficult. It's it may not be worth actually doing here, but it's something that you can assign as a problem in undergraduate courses. So you could go to your favorite undergraduate book, like the one I wrote, and you'll discover that it's assigned as exercise 11.7. So it's not that hard. You just integrate over all filled state for an integer quantum Hall state or a one-dimensional fermionic channel. You just integrate over all occupied states to get the n times the velocity of the particular eigenstate, and add it up to get the current or the energy, the heat current, and you get this quantization condition. Now, let me try to give some reason why this is interesting to measure both the electrical and thermal conductance. Here I made a table of various different quantum Hall states. These are labeled by their so-called filling fraction, which is just the ratio of the density to the magnetic field made dimensionless by a flux quantum. And so we have integer quantum Hall states, 1 or an integer n, and then we can have fractional quantum Hall states like the Laughlin state, nu equals 1/3, or the Jane series, p over 2 np plus 1. So these are a bunch of the different types of quantum Hall states that have been observed. And you can count the number of edge modes. So the nu equals 1 has 1 edge mode, nu equals n has n edge modes, nu equals 1/3 has 1 edge mode, and the Jane state written here has p edge modes. And you can calculate what its electrical conductance should be in the units of the electrical conductance quantum, and what its thermal conductance should be in units of the thermal conductance quantum. Now you'll notice that the electrical conductance always matches the filling fraction, and this is not surprising. In fact, we know that the electrical Hall conductance of a system, and a clean system, always has to be given by the filling fraction. This is a result of Galilean invariance, basically. But the thermal conductance gives us something else. It actually, in these cases, it's counting the number of edge modes. In more mathematical language, it's telling us the central charge of the bulk theory that we're looking at. Now, there's a couple reasons why it might be interesting to go try to measure the thermal conductance of a state. Here's a particularly interesting example. If you think about, so what is known experimentally is that there's a quantum Hall plateau at filling fraction nu equals 2/3, but there's at least two things that could be giving us that plateau. It could be a spin singlet or overall spinless quantum Hall state, or it could be a spin polarized or spinful quantum Hall state. Now, these two both would give the same electrical Hall conductance, but they would give different thermal Hall conductance. The 2/3 spin singlet has 2 forward-going modes, whereas the spin polarized state has 1 forward-going and 1 backwards-going modes. And so the former state here with 2 forward-going modes has 2 conductance quanta of thermal conductance and approximately 0 conductance quanta in the case of 1 forward and 1 backward-going mode. So that means it's gives us a good reason to go and try to measure the thermal conductance of certain quantum Hall states where we don't know exactly the nature of the quantum Hall state that we're looking at in the experiment. Now, when this was first proposed as a probe, that it would be interesting to measure the thermal conductance of a quantum Hall state. This is by Kane and Fisher in 1997, Kane being Charlie Kane. Once again, I am betting that Charlie Kane is going to win a Nobel Prize this fall, but I've lost this bet a number of times before, but we'll see again this year. You heard it here first. Anyway, so in 1997, Charlie Kane, before he started thinking about topological insulators, was thinking about quantum Hall edges, and they proposed that experimentalists should go out and try to measure the thermal conductance of the edges. And no one really thought that it could be done. The experimentalists basically said this is impossible to do. And there's a good reason why it's impossible to do, because you're, on a typical quantum Hall sample of that time, you have a layer of, say, 10 to the 11th electrons sitting in this thin slab, buried underneath, 10 to the 23rd atoms on either side. Now, the 10 to the 23rd atoms are still carrying heat themselves via phonons, and you somehow have to isolate the heat being carried by the electrons in this thin slab of 10 to the 11th electrons. And you have to do a lot of other things too. The whole experiment is going on at tens of millikelvin temperature, and you have to be able to measure heat the heat is put into the sample, the heat comes out of the sample, all down at 10 millikelvin temperature. This just seemed impossible to do. But 20 years of innovation later, people figured out how you could do this. And the breakthrough actually came from this experiment by a French group, and they were not actually studying quantum Hall samples. They were studying one-dimensional quantum wires, where you expect to get 1 unit of electrical conductance per channel in the ballistic wire, and 1 unit of thermal conductance per channel in the wire as well. And they showed this beautifully, and they showed how you could separate out the electrical from the phonon contribution, and how you could measure temperatures and you can measure heat all at down in the millikelvin range. And this technique really started the field moving again, where it was picked up by the group in the Weitzman who's done the experiments that I'm going to talk about today. So the group in the Weitzman was well set up to they had all there are a lot of pieces of technology that you have to have developed first, measurement of things at low temperatures, and chop noise at low temperature, and on-chip amplifiers, and lots of details, which they all had at that point. So it was, it did take them 5 years to go from deciding they were going to do this to actually getting results. But nonetheless, they were pretty well set to do it. And they started their exploration by just measuring a couple of standard quantum Hall samples. And here are the results. And I'm giving you the result in units of this thermal conductance quantum. And in this column, we have the particular quantum Hall state we're looking at, the filling fraction. And then I have the predicted thermal conductance. I've always written the predicted thermal conductance as a difference between the number of forward-going modes and the number of backwards-going modes. All the mode in this table, all the modes are bosonic. Each mode has central charge 1. All modes are on equal footing. It's just a question of whether a mode is going forward or a mode is going backwards along the edge. Now, this formula could give you a negative number, and total thermal conductance is always positive. You always have to get heat moving from net heat moving from from a hot reservoir to a cold reservoir, otherwise you're breaking the second law. That, of course, doesn't happen. What you actually measure is the absolute value of the number that I have written here predicted. And the reason it's absolute value, what it means when this number comes out negative is that the heat is basically moving, each quantum Hall bar has 2 edges. There's a sort of a left edge and a right edge. And whether this number comes out on the positive or negative is basically telling you whether the heat is going from hot to cold on one edge or it's going to hot to cold on the other edge. Okay, so it's just telling you which direction the heat is circulating. The heat always moves from hot to cold in some way. Okay. Anyway, the end result of this measurement is that within experimental uncertainty, and the uncertainty isn't pretty that big, they actually get exactly what is predicted. The number of forward-going modes minus the number of backwards-going modes, with one exception here. In this case, well, okay, so they get a number. They're expecting to get 0 because you have 1 forward. Was there a question? No. Okay, sorry.
Has the experiment been repeated?
Well, the same group has repeated the experiment, but no other group has done it.
I don't need to talk.
But I think it's not going to be long before another group will do it, because if you call it another group, the postdoc who did that, so the head of the lab is Moti Heiblum, who's been running the lab at the Weizmann Institute for decades. The postdoc, a young woman named Mitali Banerjee, who is superstar experimentalist, who then now has a professorship in I think in Lausanne, and she's setting up her lab to do this kind of experiment. So she'll have independent measurements of the same sort, whether you call that an independent reproduction or not, because it's in a different lab, but it's the same person. I don't know, but there will be competing groups doing the same kind of thing. There's a good reason why other groups haven't tried to do it, which is that there's a lot of technology that you have to develop first. Things like being able to measure noise at very low temperatures, being able to do on-chip amplification of certain types of signals, I mean, a lot of details that Moti Heiblum's lab has been working on really for 20 years. I mean, they were working on it for some other purposes, but very, very few labs in the world have this technology. I mean, once you know what it is you're trying to do, of course, it's easier to do it for someone else because they don't have to make all the same errors that were made the first time through. Probably they call up the people who did it and say, how did you do it? But still, there's a lot of development that has to go into making this experiment work. And it was really only 2 labs in the world where really had the technology to do it. One is the French lab, and one is the Weitzman lab. So that's why it hasn't been reproduced so far. Anyway, the one case where doesn't come out in perfect agreement with the experiment is at nu equals 2/3 here, where you expect to get 0, 1 minus 1. And you don't get 0, you get something that's closer to 0 than it is to 1, but it's not 0. But the claim is if you make the sample longer and longer, you'll actually get closer and closer to 0. And the claim is the sample just isn't long enough to get to 0 yet. And we'll come back to discuss this later because that's going to turn out to be an important issue. All right. So all of these quantum Hall states are so-called abelian quantum Hall states. And people are like abelian quantum Hall states, but they're not the latest and greatest. Let me explain just in a couple words what abelian versus non-abelian is. So an abelian quantum Hall state is basically a topological quantum field theory, which is based on an abelian U1 Chern-Simons theory versus a non-abelian group like an SU2 or E8 or something like that. So the difference, the functional difference between abelian and non-abelian quantum Hall states is that the quasi-particles obey either abelian or non-abelian statistics. And to give you an idea what we mean by this, you imagine having some quasi-particles in your 2-dimensional sample. You drag one, exchange 2 of the quasi-particles, and you want to ask what happens to the wave function when you exchange them. For an abelian quantum Hall state, the wave function is a simple scalar, like we usually think of wave functions, and the exchange incurs a phase which is not +1 or -1, like you would get for bosons or fermions. Incidentally, this is just a side comment, that the prediction that for the simplest fractional quantum Hall state, the nu equals 1/3 state, the Laughlin state, that exchanging 2 of these quasi-particles should give you a fractional phase. This prediction was made in 1984. And the entire theoretical community believed it immediately. And it is only this year that there's been a really convincing experimental proof of that statement. But they now have a fairly convincing experimental proof of that, as far as I can tell. So that's abelian quantum Hall states. Non-abelian quantum Hall states, it's a little bit more complicated. The wave function is a vector in a space of degenerate states. And when you exchange these particles, you're applying a unitary matrix to this vector space. Now, this brings up the application that why people like non-abelian quantum Hall states is because applying a unitary matrix to a space is something that would be very useful for building a quantum computer. And that's what people want to do with these quantum Hall states. Okay, so that's a 2-minute introduction to abelian versus non-abelian quantum Hall states. So we turn our attention to the nu equals 2/5 state, fractional quantum Hall state. It's unusual as a fractional quantum Hall state in that it has an even denominator. Very few of the quantum Hall states have even denominators. Before the 5/2 state was discovered in 1989, I think every single quantum Hall state that had been observed, about 30 of them at that time, and maybe up to 90 of them by this time. 5/2 was the only exception at that time of having an even denominator. I think by now, there's 5/2, there's 7/2. There might be 1 or 2 others that have even denominators, but all the remainder of the 90 or 110 that have been discovered all have odd denominators. It's believed that the quasi-particles of the fractional quantum Hall state are Majorana in nature, and it's believed that braiding them is that they are non-abelian, meaning that braiding them makes a unitary transformation on a vector space. So that in principle you could, in someone's dream you could do topological quantum computation. So what's not controversial is that there is a nice plateau at nu equals 5/2 filling fraction and a great big dip in the longitudinal resistance. So there is a fractional quantum Hall state at 5/2. What is a little bit unknown is what fractional, what is the nature of that fractional quantum Hall state? What phase of matter are we looking at?
Sorry, Steve. You said quantum computation, but probably the curve is too small for the 5-2.
That's correct. So it's not universal. Okay, assuming it comes out to have Majorana quasiparticles, and braiding Majorana quasiparticles is typically for any of these quantum Hall states, it does not allow you to do universal topological quantum computation. So it would make a very good quantum memory, but you could not do every operation that you wanted to do by just braiding them around each other. That's correct. Nonetheless, there's a lot of people who are interested in Majoranas for topological quantum computation reasons, where they would supplement the topological operations with some non-topological unprotected operations. There's sort of there's a story. I mean, so people are trying to build Majorana systems not only in quantum Hall, but in superconducting devices and so forth. And it's a big field which Microsoft is investing tons of money into. Most of the, almost all the research is aiming at systems that would not be universal by braiding particles, just by braiding things around each other. But the argument is that if you can do certain operations which are not completely universal by themselves in a protected way, very accurately, then the amount you can get the other operations wrong by, so the resilience to errors in the other operations goes way up. So your other operations, your non-topological operations, can be much worse if you have a set of topological operations that are very accurate. That's the idea. Okay.
Just one other thing is there any other option theoretically for the 5/2?
Yeah, I'll give a list of what of some of the things people have suggested for 5/2 in a moment, and what we think theoretically about it as well. Okay, so
sorry,
for 5,
if they are Majorana, what is a non-abelian group?
Yeah. So there's this. It's a spinor representation of SON for some large n or something like that, where you get. I mean, one way to imagine what the Majoranas, when you say the unitary operations that you can perform, can be thought of as you take a very large real vector space and you can do 90-degree rotations along any axis. That's the group.
Okay.
Okay, that it is isomorphic to that.
Yeah.
So, okay, so for a 5/2 state, you would expect to have a Majorana edge. And Majorana is a half a fermion. It takes 2 Majoranas to make a Dirac fermion. And that means that we should get a half unit of thermal conductance. Okay, so that's the prediction. It's made.
Easy.
Sorry, I didn't hear this. Was there a question? Okay, no. Okay, so this is the next experiment that the group in the Weissman did, and they claim to have measured a half integer thermal Hall conductance, which would be exactly what you expect for having a Majorana edge. Okay, so again, Matali Banerjee was the main author, the main postdoc who did the work. Moti Heiblum, the head of the lab. Vladimir Umansky is the crystal grower, and then the 3 theorists on the experiment as well. So here's a list of some of the things that have been proposed for the 5/2 quantum Hall state. So a lot of different possible states of matter that people have mumbled could be responsible for the plateau at 5/2. The ones in blue have Majorana edges. And you'll notice that the predicted thermal conductance for all of the ones in blue are something 0.5. And the 0.5 is always given to you by the Majorana mode, which contributes a half, either plus a half or minus a half, depending on its direction. So it's quite a lot of possibilities. which one of these do we actually think is realistic? So this is a rather long story. And so the story starts way back in 1989 when the 5-half state was first observed, and there was about a decade of confusion about what was going on, and it was straightened out to a large extent by Rudolf Moore in 1998, who showed some extremely good numerical data, basically exact diagonalizations on small systems with appropriate extrapolations and so forth, which suggested that what was going on at nucleus 5/2 is a so-called Moore-Read Pfaffian state. And for those who like conformal field theory, this is based on an Ising conformal field theory, or an Ising conformal field theory if you pronounce it correctly. And the reason why it went 10 years before people came to this conclusion is because there were some red herrings, which really are more experimental in nature, that made people confused about what was going on in the experiment. And this data looked extremely good. And after Morph, there was about a decade of lots of numerics being done by a lot of people confirming what Morph had said. Now, a little bit thereafter, in the year 2007, it was proposed that actually Morph's data would be just as consistent with what's known as the Anti-Pfaffian. So the Anti-Pfaffian is exactly the same as the Pfaffian, but it's particle hole conjugate within a Landau level. So the way to think about this is you fill up you have a half-filled Landau level. So you start with you can imagine starting with an empty Landau level and filling it half up with electrons. That gives you the 5. So you start with nu equals 2. That's 2 filled Landau levels, and you half fill the valence Landau level with electrons, and you put those electrons in the Pfaffian state. That gives you the Moore-Read Pfaffian. But another thing you could have done is you could have filled 3 Landau levels and then removed half of the last Landau level, half of the valence Landau level, kept track of where you put the holes, and put the holes in a Pfaffian wave function. That gives you what's called the Anti-Pfaffian. So these two are mirror images under them, under the transformation of changing a particle to a hole within the valence Landau level. And the reason that these would be exactly, this would be equally in agreement with Morph's data is because typically when you do exact diagonalization on small systems, you work with a system that has complete particle hole symmetry. And pure Coulomb interaction has complete particle hole symmetry when restricted to a single Landau level. So there would be no way to distinguish from Morph's data whether you're looking at the Pfaffian or the Anti-Pfaffian in the experiment. So both of these were equally in agreement with the experiment. And this is another thing that it's extremely surprising that it took until 2007 before people realized that the Pfaffian and the Anti-Pfaffian are actually different phases of matter, and they have different properties. And they're equally in agreement with the experiment. So the Pfaffian versus Anti-Pfaffian, the question of whether things are half empty or half filled. So, the status of the numerics is basically that the Pfaffian and the Anti-Pfaffian are both competitive with each other, and pretty much everything else is completely excluded by the numerics. The numerics say that everything else is terrible. The Pfaffian and the Anti-Pfaffian are both pretty good. And then Ed Rezai and myself, starting in 2009, started to try to add back in the very weak particle hole symmetry breaking terms that would distinguish between the Pfaffian and the Anti-Pfaffian experiment. And in 2009, we found that the Anti-Pfaffian was favored. And then there was a series of papers by some other authors claiming the opposite result, that the Pfaffian should be favored. And to be honest, I couldn't figure out why it was that certain ways of addressing the problem got one answer, and certain ways of addressing the problem got another answer. I gave up on it out of frustration, but Ed Rezai is extremely tenacious. And in 2017, he actually found out why it was that certain ways of addressing the problem seemed to give a different answer than what we had originally gotten. What we had originally gotten actually turns out to be correct, that when you add back in the weak particle hole symmetry breaking terms, the Anti-Pfaffian is slightly favored over the Pfaffian. So that's what we expect theoretically from the numerics. So now let's turn to the experiment.
Sorry, Steve, can I just ask a question before you leave that slide?
Yeah.
Is the Bose condensate of composite fermions one of those? Is that ruled out now as a possibility? Bose condensate of composite fermions, that used to be a possible a candidate for the 5/2.
So I'm not sure what that would be. It doesn't have a name that's on this list. Oops, hello. Can you hear me?
Yeah.
Yeah, okay. So I'm not sure what Bose condensate of composite fermions would be on this list. Composite fermions are fermions, so they don't Bose condense. So you have to do something to them first before you Bose condense.
Oh yeah, it's like it's pairs. They pair to give bosons. Yeah.
So okay, so Pfaffian and Anti-Pfaffian are both can be interpreted as BCS pairing of composite fermions. So they're different. They're different.
So these are examples of that model then. I see. Okay.
These are examples of that. They're different pairing symmetries. In fact, Pfaffian, PH Pfaffian, and Anti-Pfaffian are different pairing symmetries of pairing of composite fermions.
Okay, good.
Okay. All right. So here's the experiment. Here's experimental data, and this is a function of temperature on the bottom in millikelvin, and this is thermal conductance in units of the this conductance quantum. And okay, so it's not perfect, and you'll notice that it seems to hover around 2.5 at some temperature range up here. I think there's one more point up here, which I don't have on my plot because it was, well, it was not in this version of the data. I think a later version of the data had one more point, but it's sort of imagine another point over here. And you'll notice that at lower temperature, it seems to deviate somewhat from 2.5, but the experimentalists claim that at least for some region, it seems to be pretty close to 2.5. So they declare victory and say, okay, 2.5 quanta, so we have a Majorana. So this is half victorious for measuring the half quantum. It's also half puzzling. And so we'll come back to this issue down here of it deviating from 2.5. Also, the different colors of the points, they change the filling fraction a little bit to make sure it's not that sensitive and things don't move around too much as long as they stay on the quantum Hall plateau. So that's a good sign. And they also say that they don't see any heat flowing through the bulk. That's a good sign as well. So they're seeing edge transport and 2.5 quanta worth more or less. But it's also half puzzling. Why is it half puzzling? Well, 2.5 is not one of the two things we expected to happen. We really expected 1.5. That's what the Anti-Pfaffian would have given us. And that's what's favored according to the numerics that Ed and I had done. And if it wasn't that, the other one that's competitive is the Pfaffian, which is 3.5. All the other phases of matter that have been proposed are excluded by numerics. They're terrible in numerics. Their energies is just awful. Was there a question? Okay. No. So we're getting this other thing, is 2.5, which seems to be, out of the question, given the numerics that have been done. Now, I should give credit to the people who thought up this thing, the PH Pfaffian. It was thought up by Damson, but it was based on earlier work by Fitkowski, also Bonderson and Berkeshly and Wan and Yang. It's basically a sort of a particle hole symmetrized version of the Pfaffian and the Anti-Pfaffian. It can be thought of as a different pairing symmetry of the Pfaffian. The Pfaffian is perfectly particle hole symmetric, which is what the PH stands for, particle hole symmetric version of the Pfaffian. Now, how is it possible that our very, very clear numerics got the answer so wrong? The numerics that tell us that the PH Pfaffian is excluded are not subtle. Maybe the numerics that tell us that the Anti-Pfaffian is better than the Pfaffian are fairly subtle, but the numerics that tell you that the PH Pfaffian is terrible are not subtle at all. So how is it that we got the answer so wrong? Well, the numerics have no disorder. That's one possibility. And we might ask the question, it's very hard to do numerics on a small system with disorder. Disorder just would dominate everything. So you always use clean systems when you do small system exact diagonalization. And the real system has disorder in it. So is it possible that the presence of disorder changes the balance somehow and makes the PH Pfaffian favored? So this got a lot of people thinking. I mean, my first reaction to this is, you know, the pH Pfaffian is so bad, there's no way this could happen. But then people started thinking up some schemes where it looks like it might be plausible. So the schemes tend to go like this. So, you know, the Pfaffian and the anti-Pfaffian are sort of competitive in their energies. So let's imagine that you have a case where you have domains of Pfaffian and domains of anti-Pfaffian. So this picture was made by 3 groups, actually, really 2, and then the one following a little bit thereafter. The Weitzman group, the Harvard group, and then a group at Princeton as well. So imagine you have regions which are Pfaffian and regions which are anti-Pfaffian. There would be you know, domain walls where heat flows along the domain walls. There would be Majorana edge modes running along the domain walls. So one possibility here is that these internal edge modes percolate across the system, in which case you would have what's known as a thermal metal. This is sort of the most generic thing that you could imagine happening, which would be different. You would get, since the Pfaffian and the anti-Pfaffian have the same electrical conductance, and the domain walls in between are neutral, they carry no electrical current, you know, this thing would electrically look like a perfectly good quantum Hall state, but thermally it would carry heat through the bulk along these neutral domain walls, these Majorana domain walls, and you'd get unquantized thermal conductivity. And if you look back at the data, you might say, well, the thermal conductivity, it's not that well quantized. So maybe that's what's going on. You're getting quantized electrical conductivity. They say the electrical conductivity is very well quantized, but you're not getting quantized thermal conductivity. Now, I think the experimentalists would disagree with this. And the reason they would disagree with this is because they have an ability to measure how much heat flows through the bulk, as well as measure the heat flowing along the edge. And to within, you know, the precision with which they can measure, they say no heat is flowing through the bulk. And with this picture here, you would have to get heat flowing through the bulk. So they presumably think that this is not the right answer. So maybe there's some additional story which we don't know yet, which would explain why it is that you get heat flowing through the bulk, but not much heat flowing through the bulk. So it would be a metal, but a really bad metal or something like that.
There's also systematic growth as the temperature is increased.
Yeah, so that's one of the issues as well. I mean, it seems to be definitely going up as you go to low temperature. So we're gonna have to explain that as well, which some other models might, as we'll see as we go on. So just the fact that it's unquantized doesn't necessarily explain why it should be going up instead of going down. Maybe a more microscopic picture of that, you know, maybe someone could come up with something that would do that. But the thing that these 3 groups really wanted to ask is something a little bit more subtle. Is there some way you can get these domain walls to couple together and then gap out in such a way to create a quantum Hall state, both electrical and thermal, something that's fully gapped to both electrical transport and thermal transport? If you could do so, you would necessarily get the pH Pfaffian, or you'd have to get something that's particle Hall symmetric, because this is exactly as much Pfaffian as it is anti-Pfaffian. You have a bulk system which is exactly symmetric between domains of Pfaffian and domains of their particle Hall conjugate, the anti-Pfaffian. And if you could then somehow make that whole thing melt into one quantum Hall state, it would have to be particle Hall symmetric. And the pH Pfaffian is the only thing on that list that it could be. And you could then argue why it has to have the topological properties of the pH Pfaffian over long length scales. So the answer to this appears to be yes, but. Yes, you can do this. You can arrange such that you can gap out these internal edge modes by arranging very special type of scattering at these sort of saddle points. But generically, you have to fine tune things in order to get that to be true. And there's a statement from the Wang, Halpern, Vishwanath group at Harvard that generically our network model does not favor this behavior, that it would require some fine tuning that they have no reason to believe is true. I mean, the fine tuning in particular is that each of these domain walls here carries 4 Majorana modes. And then if you come to a saddle like this, you have 4 in here, 4 in here, 4 out here, 4 out here. So you have some sort of 8 by 8 scattering matrix. And only if you fine tune that 8x8 scattering matrix at every saddle can you get this behavior, is what they found. Okay. So that looks pretty bad, unless there's some reason that it self fine tunes to this special point. But before we ask this, whether this is a possible solution, we should ask, okay, so the conclusion here is that we should expect either a thermal metal, which is sort of generic, or unlikely you get a pH Pfaffian from this fine tuning somehow. But first we should ask, why should we ever expect to have domains in the first place? The input to this theory is that you have domains of Pfaffian and domains of Anti-Pfaffian. Why should you have domains? Is there any situation in which you could expect to get domains? Well, this argument, again, from the Halpern collaboration at Harvard, gives you an argument why it is you might expect to get domains so generically. It goes like this. So I'm going to draw things that are lower energy as being green and things that are higher energy as being red. If you're right at filling fraction 5/2, so there's no stray quasi-particles or anything like that, no disorder, then the Anti-Pfaffian is lower energy and the Pfaffian is higher energy. This is what we found numerically. Now, then let's add some quasi-electrons to the story. We're going to shift the filling fraction a little bit. So we're adding a couple of additional particles. We add these additional particles, and it happens to be the case that the quasi-electron particles, these quasi-particles of the Anti-Pfaffian, are higher energy than the quasi-particles of the Pfaffian. So once you go slightly off the center of the plateau, then you get some lower energy things over here on the right picture, on the Pfaffian picture, and you get some higher energy things over here on the left picture. If you go far enough off the center of the plateau, the picture on the right will be more green than the picture on the left, and the net energy balance will be better to be Pfaffian with particles added than to be Anti-Pfaffian with particles added. And so it switches. So you might imagine that if you go slightly away from nu equals 5/2, you shift the filling fraction a little bit, then the energy balance changes and the Pfaffian is lower energy. So if you have a sample where the density is slightly non-uniform, you might be able to tune the filling fraction just so there are certain regions where the Anti-Pfaffian is favored and certain regions where the Pfaffian ends up being favored. Now, this sounded like a good argument, but we wanted to take a little bit more careful look at this, and this is the content of this paper. And we looked at how many quasi-particles do you actually have to add to the Pfaffian in order to change the energy balance. And what we found, well, right down here, we concluded that for parameters appropriate to recent experiments, such domains would not occur. Parameters appropriate for recent experiments, such domains would not occur, is our conclusion. So we believe that we killed the idea of mixed domains of Pfaffian and Anti-Pfaffian. And the reason for this is simply that it is true that the Anti-Pfaffian quasi-electrons are higher energy than the Pfaffian quasi-electrons. And if you add enough of them, you will switch the energy balance. But the key point here is in the word enough. The enough that you have to add is so many that you'd be way off the plateau anyway, and it just wouldn't be in the same quantum Hall state. Now, I thought this was pretty definitive, but then another paper came out by Donna Sheng and Kun Yang and their postdoc, and they pointed out that we had missed something, and I will admit that we had missed something, that the domain walls have a electrical polarization. This is not an obvious fact, but it's true. The domain walls have an electrical polarization, and it is possible that the domain wall, if there's electric fields in the sample due to impurities, that the domain walls could arrange themselves to stabilize a situation with multiple domains. And that could change the energy balance and then make the presence of multiple domains favorable again. Now, this is something that it would require, we're trying to balance some bulk energy with some boundary energy. And so the domains here would have to be pretty small for this story to make sense. You'd have to have fairly small domains and fairly large electric fields in the sample, but it didn't seem to be completely out of the question that such a thing could happen. So Ed Rezai and myself have been back in the drawing board trying to see whether there's any circumstance in which this story actually will hold water. As of yet, our tentative conclusion is that that it still won't work, that you still can't get multiple domains, but we're withholding complete judgment still.
But Steve, wouldn't you expect the domains to grow in size as you decrease the temperature? Which
not necessarily.
The opposite trend?
You might. So the domains would be dictated. I mean, you're thinking about to annealing of domains where you have domains sort of joining together. But this is not necessarily what's going to happen, because there's a frozen in disorder that's pinning that some particular area has to be anti-Pfaffian, because that's where the disorder is appropriate for the anti-Pfaffian, and some particular region has to be Pfaffian, because so that's the fact that even at zero temperature the domains could be very small is something that's possible.
Steve.
Yeah.
So could you not just force the state to be completely Pfaffian by going slightly off the filling fraction?
To go completely Pfaffian. Yeah.
Yeah. I mean.
Yeah. But if you did that, you would get something that didn't agree with the experiment also.
No. I mean, in the experiment, you might be able to try that.
Oh yeah. So in the experiment, they do not see any. So this is another reason why it doesn't seem to be a very good answer. That they do not see the. I mean, you would think in these pictures where you have domains, it should be very sensitive to where you put the filling fraction. If you put the filling fraction a little lower, it should go to all anti-Pfaffian. A little bit higher, it should go to all Pfaffian. And it's only somewhere in the middle where there's a regime where it's this mixed domains.
Right.
They do not see the thermal conductance going down to 1.5 and then up to 3.5. In the middle is 2.5.
Yeah.
So that is
not good.
Not good for that explanation. But it's we don't have they don't have a better explanation at this point yet either. Right. So we're sticking with that. Okay. So is there another solution? Well, of course I wouldn't be giving this talk if I didn't think there was. So full disclosure of this story. I was the referee for the paper that published the experimental results, and they had concluded that this must be the pH Pfaffian. And I wrote back to them and I said, look, I think there's another explanation that's possible and that you should mention. And they wrote back to to Nature and they said, we do not believe that's possible, so we're not going to mention it. And I said, I give you one more try. You have to either mention it or I'm going to write a paper about it. And they didn't do it, so I wrote a paper about it. So so this is my interpretation. And there's a good reason why they didn't like this explanation, but I'll explain to you why it's not really as bad as it seems. So my solution is that we're going to just assume it's the anti-Pfaffian, okay? The whole thing is anti-Pfaffian. That's what the numerics tell us it is anyway, in the absence of disorder. I mean, there's not that much disorder in the sample. The samples are very clean. So let's pretend it's anti-Pfaffian. Now, the problem we have is that anti-Pfaffian predicts 1.5 units and they measure 2.5 or something close to 2.5. So is there a way that we can get 2.5? So we need to think a little bit about the detailed structure of the anti-Pfaffian edge. So just to tell you how this works, so you start with 3 filled Landau levels. Each one of those 3 filled Landau levels has one edge mode going forward. Then you remove from the top Landau level the Moore-Read Pfaffian. So that has a bosonic mode going backwards and a Majorana mode going backwards. So it's 3 forward, 1.5 backwards. That gives you 1.5 total. That gives you the prediction of 1.5. But why did we subtract? Okay, well, in all of these cases, we subtracted and we got the right answer. We always took forward going modes minus backward going modes, except, and why is it that we take forward going modes minus backwards going modes? Well, the assumption is that all of the edge modes, multiple edge modes, thermally equilibrate with each other. That means at any point along the edge, all of the edge modes agree on what the temperature is at that point. And a different point along the edge, they all agree on what the temperature is, and they also agree on what the gradient of the temperature is. So the only difference between a forward going mode and a backward going mode is they agree that the gradient of the temperature is pointing this way, and if you're a forward going mode, then you carry heat this way, and if it's a backwards going mode, you carry heat going this way. So you add up the currents with their signs. Forward-going modes carry it this way, and backward-going modes carry it this way. So you add up the conductances with their signs. However, if the edge modes don't talk to each other at all, the conductances had better add an absolute value. Why? It's just a couple of resistors in parallel to each other. There's two routes for the heat to get from hot to cold. It's like two resistors carrying current from high potential to low potential. And if they don't talk to each other at all, then they have to add their conductances in absolute value. Because, independent of which way the heat is flowing, it's always carrying from hot to cold, one way or the other. In this situation where the conductances are adding in absolute value, the two edges will completely disagree on what the temperature is. A forward-going mode will have the temperature of the left contact, and a backward-going mode will have the temperature of the right contact, and they'll completely disagree on what the temperature is all the way along the edge. But because of that, now the conductances add an absolute value, and that's exactly what's going on in the nucleus 2/3 state. We're getting non-equilibration of the edges, and that's why we're not getting the difference of 1 minus 1 exactly coming out to 0. It's coming out to something non-zero. If you make the edge really, really long, that gives the edges a better chance to equilibrate, and this number will come down to 0. But if you make the number really, really short, then it gives these two edges no chance to equilibrate, and instead of getting 1 minus 1, you get 1 plus 1. You get 2 units of thermal conductance over very short distances. And this is known physics. Okay, so
sorry, is there a temperature sensitivity on those numbers?
On this number, yes, there is. So this number will change as a function of temperature, and actually it gets closer to 0 as you go to higher temperature because the equilibration length drops.
So it goes on the same trend as
yeah, exactly. So this is a good sign of what's going on. So my claim is the following. Let's suppose that these 4 edge modes are thermally equilibrating, but the Majorana mode is not. So then we have 3 minus 1 modes over here, all agreeing on what the temperature is, and then 0.5 not agreeing on what the temperature is. So then we have 2 from all these modes, 3 minus 1, plus 0.5, adding in parallel, back up, adding in parallel to give us 2.5. Now that sounds pretty easy. And you say, well, why isn't it that these highly respected theorists who are co-authors on the paper, why didn't they think of this? Well, there's a good reason why they did think of it, and there's a good reason why they rejected it. So the reason they rejected it is the following. We know that there has to be backscattering of electrons from the valence Landau level to the boson and Majorana mode, okay? If they didn't have that backscattering, then you would not get quantized electrical conductivity. You have to be able to electrically equilibrate these 4 edges. Now, the electron, when it scatters into the fractional quantum Hall state, it breaks up, it fractionalizes into a Majorana and a boson, okay? So when this electron backscatters, it has to put something into the Majorana mode, okay? So on the one hand, I'm saying the Majorana mode is not thermally equilibrating with the others. On the other hand, in order to get quantized electrical conductivity, I know this backscattering is occurring. So now I'm asking for something that seems a little unlikely. You have to have backscattering into the Majorana mode, but all the heat is going into the boson mode, not into the Majorana. So when this fractionalization occurs, the fractionalization occurs in a very non-generic way. The heat goes entirely into the boson mode and not into the Majorana, okay? So this seems a little bit difficult to justify. Now, after this paper, there have been several different, let me skip the explanation because I realize I'm using a lot of time, but there have been now a number of different proposals as to how you could get this physics to occur. None of these proposals are without problems, but they're not crazy either. So in the original paper that I published, I said that, well, the Bose velocity and the Majorana velocity are known to be very, very different by a factor of 10 or so. And that really can affect how much heat goes into the Bose mode versus the Majorana mode. And under certain conditions, you may be able to get all the heat to go into the Bose mode, and therefore it would be consistent with the experiment. Then there was a comment from one of the authors of the paper, Dima Feldman, saying, yes, there's a large ratio of the Bose to the Majorana velocity, but in fact, it's not big enough. It's not a big enough ratio to explain the experiment. And then they had another paper themselves that they proposed shortly thereafter, which also used the large velocity contrast along with some other things to try to justify a non-equilibration mechanism like this. There's a very beautiful paper by Asasi and Mulligan, which points out that there's an infrared fixed point. It's hard to tell whether we're anywhere near that fixed point, but that fixed point could also potentially explain the experiment. Then I have a paper with Bernd Rosenau describing a particular mechanism, Majorana-assisted tunneling, which can, in a rather natural way, potentially explain the data as well. And maybe, since I realize I'm pretty close to an hour, let me try to, should I go
There's
over?
No need to rush through. You go over, please.
Okay,
Don't
go over. Okay, so I'll go through this fairly quickly. It's
being recorded, so if people miss something, they can go back and get it. Whereas if you don't put it at all, we won't have any offer.
So the mechanism is like this. So we want to study the backscattering of an electron into the Bose and Majorana mode. We start by ignoring all of the disorder and asking, can backscattering occur? And the answer is that backscattering cannot occur because in a magnetic field, motion in one direction, x displacement in one direction is a momentum displacement in the perpendicular direction. So in order to scatter from this position to these positions, you need to break translational invariance in the x direction. So this is forbidden by translational invariance along the edge. Okay, you cannot backscatter at all. So I need to break translational invariance to get this backscattering. Okay. Usually what people do is they just add disorder all the way along the edge, but I'm not going to do that. I'm going to say, let's imagine the edge is very clean. I'm going to add one remote localized Majorana in the bulk. Because we know these localized Majoranas exist. Every quasi-particle carries a Majorana. So we'll just sit one in the bulk, say he's trapped somewhere in the bulk, and he's going to have some tunneling strength to the Majorana mode at the edge. And that is going to break the translational invariance, this tunneling between the bulk at some position and the edge. Now, what does this do? What this does, okay, don't need that, oops. All right, you're gonna see the funding opportunities. So if you just solve the problem of a Majorana, a one-dimensional fermionic edge with a single impurity, basically this is done in some standard textbooks like Mahan's book, you'll discover that as you go by this localized Majorana, there's a phase shift. And the phase shift is 0 at high energy. I mean, it's 1, or the identity at high energy. It's, it completely ignores the localized Majorana if the Majorana edge is at high energy. But you get a maximum phase shift of -1 if the Majorana is coming along with low energy, okay? So what does this do? This tells me that the scattering occurs only if the Majorana has low energy compared to this tunneling. If the Majorana had high energy, if the Majorana along the edge has high energy compared to this tunneling strength, then translational invariance isn't broken and the scattering cannot occur. So it's sort of an interesting situation where you have to break the translational invariance, and the translational invariance is only broken at low energy, which means the scattering only occurs if the Majorana gets a very small amount of energy. So this gives a natural mechanism. I mean, then you can do a more detailed calculation, and you're helped out by a factor of 32/9 pi cubed. And you find out that the energy going to the Majorana divided by the energy into the Bose mode is basically the tunneling strength divided by T times 0.1. So this will then give you what you need, which is electrical equilibration without thermal equilibration. At some low temperature, the scattering it turns off entirely at this point, and Then you have a different situation. Scattering turns off. You have 3 plus 1 plus 0.5, and it goes back up to 4.5, which is much higher. And eventually the electrical conductance becomes non-quantized too. So this is the actual, if you put some real flesh on this theory, these are the same data points, just plotted with a different program. So this is the exact same problem, same data, and it's been fit to this theory where, okay, we have to put a lot of parameters into this theory, and I've put 2 different sets of parameters into the theory, the blue dotted and the red solid, just to show that it's you know, independent of some of the parameters to some extent. You have to put in things like what are the edge velocities, what's the coupling to the Majorana, how many scatterers do you have per unit length, what's the momentum mismatch along the edge. But these parameters are not completely unreasonable. They're not crazy, and you get something that's not too different from the experiment. So it seems plausible that something like this could explain the experiment. So the last thing is, you know, I told this this proposal to Bert Halpern, who liked the idea, and it, you know, being that he's Bert Halpern, he thought for a fraction of a second, and he said, oh, well, there's a natural experiment that the experimentalists could try, and to see if equilibration is the problem. And the experiment is to add floating contacts along the edge, just add, you know, chunks of metal along the edge of the sample, such that, you know, the electrons, you know, along the edge go into the contact. They, you know, run around with each other and they thermally equilibrate. All the edge modes thermally equilibrate before they come out again on the other side. And so this is basically forcing the edge modes to thermally equilibrate with each other, and you should get a different result for the thermal conductance. Now, it turns out that it's not as, and it sounds like it's a really easy modification to the experiment, but after discussing with the experimentalists, it turns out that although conceptually this is a very easy experiment to do, it turns out that it would muck up some other things that are kind of crucial to the experiment, and they can't do something exactly like this. But they are testing in some detail whether, you know, non-equilibration of edges is an important part of the theory. And it seems as if, as an important part of the solution, it seems like that could be confirmed, that equilibration is one of the issues. Okay, so I don't want to go through the actual details of the calculation. Let me just put up the summary. I mean, I guess I should say, you know, maybe I didn't emphasize enough that the actual measurement is you know, experimental tour de force to do this. You know, the fact you can do it at all is absolutely incredible. The observation that that nucleus 5/2 does not match the expectations that we had, is probably not Pfaffian, anti-Pfaffian domains. It is probably not a thermal metal. It is probably not pH Pfaffian. It could be the anti-Pfaffian with the Majorana mode remaining out of thermal equilibrium. There's at least one mechanism that could potentially give this, although I wouldn't bet my life on I would bet a lot more on non-thermal equilibration being part of the solution than I would on this particular mechanism being the right mechanism that allows for thermal equilibration but not electrical, that allows for electrical equilibration without thermal equilibration. So I guess I will stop there, and thank you for your attention. Any questions?
Yeah. So what about trying making prediction for some other state with Majoranas?
To try this for some other state with Majoranas? Was that the question?
Yes.
Yeah. So there aren't many to play with. Another possibility is the 7/2 state, which is supposed to be, you know, pretty much a mirror image of the 5/2 state. The reason that 5/2 is a good one is because it's quite strong in the experiment. And really the other ones that had been proposed as having Majoranas are extremely weak, or maybe not even present at all in all but the very cleanest samples. So they're using Majorana, the 5/2 state to look for Majorana edges, because it's quite a strong quantum Hall state as compared to most of the others. So that's why they haven't tried it on other states. They did think about trying to do some measurements on some of the other exotic states that are seen, but I don't think they have any definitive results on those yet.
Yes, but still, well, maybe it will be possible in 10 years, but you should make a prediction.
Oh, yeah. So, okay, so one state that also gives some kind of weird results is 8/3, which is close to the 5/2 state. That actually may be a hint. That it seems to be having trouble equilibrating as well. Now, making a prediction for what thermal conductance you have along the edge is well, one prediction is fairly easy in the sense that if you know what quantum Hall state you're looking at, you just add up the central charges with their, you say if they're equilibrating, then you just add up the central charges with the sign, and if they're not equilibrating, you add up the absolute value of the central charges, and you say, okay, there's my prediction. But in the cases where you don't know what quantum Hall state is there, then the prediction is much harder because you need to make some sort of prediction as to which of many possible quantum Hall states that you think is there anyway. And then for example, for the 12/2 state, 12/5 state, there's it could be a Jane state, or it could be a Reed-Mazai state, and those would be distinguished by their, thermal conductance along the edge. And so you have to then make a numerical prediction of which one of these two that you think should be there, and so forth. So I think the basics of that have sort of already been done. Okay. I mean, people have predictions as to which quantum Hall states are realized at least some set of quantum Hall plateaus. So there are, in essence, some predictions out there. Yeah.
Sorry.
Excellent. Thanks very much, Simon. I got interrupted just as you were finishing there, so we're into questions. Please go ahead.
Can I ask you a question?
Thanks.
Yeah.
There was this
wow.
SU2 subscript 2. Is it the quantum group you are writing there?
I think, yeah, essentially it's the Chern-Simons theory that I'm writing there. Actually, this is you can get a pure SU2 level 2 Chern-Simons theory out of Xiaogan Wen's Parton model.
Okay.
Yeah, essentially equivalent to the quantum group. Yeah.
Last one.
You mentioned the 8/3 state.
Yes. Yeah.
Is there a direct transition from 8/3 to 5/2? Can you go straight from one to the other?
There's incompressible. There's a bunch of things that occur in between. There's compressible regions in between, and there are often striped states that occur, or what we believe to be striped states, or anisotropic states that occur in between as well. So it's not a direct transition between.
Thanks.
Joost, I think you were trying to get
Yeah, I had one. So in principle, you could at least try and find the total number of modes by just making the equilibration worse in the experiment.
That's what the by making it worse.
Yeah. So this if you lower the temperature, for example, you see in this case that it goes up. Now there's probably a limit how low you can go, because at some point you're injecting heat and
yeah. No, that's right. Actually, there's room to complain about trying to make measurements at 10 millikelvin, because they actually have to put in a fair amount of heat. And you might say, well, actually, it's not 10 millikelvin; it's really 14. But they're pretty careful about trying to get what they're actually doing is they're trying to extrapolate signals down to low temperature.
Right.
So it's kind of complicated. Yeah. So you expect that equilibration gets worse as you go to lower temperature. And that's one sign of that seems to agree with, the fact that it's changing as a function of temperature is, more extremely as you get to low temperatures, it seems to be in agreement with the, change in equilibration, getting worse as you go to low temperatures.
There's no chance of driving that to saturation and finding the actual.
Well, they haven't been able to go to much lower. I don't think with this technique they will be able to, because I don't think they'd be able to measure enough heat.
Or you could make shorter bars, I guess.
Well, okay, that's yeah. You're saying that making the equilibration,
as bad as possible, so that you see all the modes add up in absolute value.
Yeah. No, it's true. It's true. Yeah, they could try doing shorter bars. That would be probably useful. That would probably be a good sign. I think this is what actually Modi's been doing in trying to check the equilibration. I mean, one of the things that's problematic though is this issue that the electrical resistance doesn't seem to change as a function of temperature. So whatever.
So you still have equilibration there, yeah.
Yeah. So you still have electrical equilibration, or at least it seems you do. But this is what he's playing with. He sent me some preliminary data where they can change the length of an edge, in real time by getting some region off and then putting it back. And I mean, these experiments are not completely holy, because you can argue, well, the nature of the edge is different when it's gated this way versus that way, and that could have some effect. Right. But at least it's sort of the at lowest order, it looks like that equilibration and non-equilibration could have something to do with what's going on.
Okay.
Steve, do you have a kind of an intuitive or hand-waving explanation for how the Majorana doesn't couple, or thermally couple?
I don't actually. I mean, you could argue that, look, the Majorana is neutral, right? So, and all the other modes are charged. So it's the fact that it's not playing with the others in a easy, in a simple way is maybe not so surprising that it doesn't follow quite the same rules. I mean, that's one possible reason. It's also a lot slower because it's neutral and the others are charged. It moves a lot slower than the other modes, and that could have something to do with. I mean, I think they're in this paper by Asasi and Mulligan, he argues that the Majorana can be very decoupled because of the mismatch in velocities. Some sort of lack of resonance between scatterings or something.
I mean, is it possible just to see, even in terms of how it would be local, like how local it would be, or is there?
Yeah, I mean, okay, I agree. This kind of thing would be great in terms of some sort of numerical evaluation of the structure of the edge and trying to see where's the. I mean, it would be nice if we could say, look, the Majorana mode actually lives way over here, and the Bose mode is living way over here. It turns out, I mean, there's been a little bit of work on trying to do something like that by the Banerjee people, Zalatel and Among company, and Zalatel has a lot of data that's unpublished. The problem is it's very hard to interpret what's going on. Mm-hmm. It's very hard to see exactly where the modes live. You have to be quite clever about trying to extract this information. It's probably something that could be done, I think. I mean, if you're tricky enough and clever enough, you can probably pull out this some sort of STM-like looking map of where this mode lives, but it hasn't been done yet.
Okay.
Yeah.
One other question, if there's nothing directly to the 5.5, you talked about the pretty recent results in the 1/3 states with the anyons. From the news, I gathered that you have good contacts to that group too. What are they up to now? And because there are many ideas of what you could do next.
Yeah. So actually, I have some contact with that group. There's a conference, there's an online conference going on in next week or the week after. And part of the purpose of this conference is to it's just a one-day thing, the virtual online conference something series being run by Mesan Barkeshli. And part of the purpose is to sort of stress test that experiment. And I mean, my feeling was that experiment is pretty darn good. But Modi Heiblum, the head of the Weizmann lab, was a little bit critical of some of the pieces. Now, I felt that his criticisms were a little bit misplaced, and experimentalists can be very mean to other experimentalists, and but these guys really know what they're talking about sometimes, and if he thinks there's some potential issue, it's worth digging down at least a little bit to see if it could cause an issue, because it is a really important result, and when you have really important results, it's good to really confirm them extremely well. So I think this particular experiment is going to be stress tested pretty hard by a lot of people before we accept it 100%. I mean, I'm very tempted to accept it 100% already, but I'm certainly willing to listen to people who think there are problems. Now, so I think one of the things that the group wants to do immediately is to back up anything that people think is questionable, because they're able to do this in multiple samples, and they're able to blah blah blah, and anything that someone thinks is a little questionable, they're going to go back and recheck. But there are already some things that look a little mysterious. I believe, if I remember correctly, the data for nu equals 1/3 looked beautiful, but 2/3 looked very mysterious. Things did not seem to work the way you would predict, and so that's going to take a little bit of thought. Maybe we just have to think about 2/3 a little bit more carefully before we conclude that there's a problem. But as of yet, the data at even at 2/3 is not completely understood. But the next thing to obviously do is to try some less trivial filling fraction and make sure that we understand what's going on there. And then obviously he's going to go to 5/2 and try to do 5/2. That would be the big fish. But 5/2 is, interferometry experiments at 5/2 have a lot of complications in them, as we've discussed. I mean, there have been people trying to do these experiments at 5/2, exactly the same kind of braiding experiments that they've now done at 1/3. People jumped to do 5/2, and they found that layer upon layer of difficulty in interpreting what's going on. And there's, so even if they could do the experiment right now at 5/2, it's because the nature of the complexity of what, trying to do braiding with non-abelian particles, it's not so obvious that they would get data which is as nice as what they've been able to get at 1/3, even if everything works out, in the most optimistic way.
Thanks a lot.
Sure.
Any other questions before I stop the recording?
Okay. Great.
Okay. Good. Thanks a million, Steve. That was
really
brilliant.
fun. I enjoyed it.
Excellent talk.
Okay.
I'm going to stop the recording and we can continue.